So let's look at this problem, a well-known problem, which is called the ballistic pendulum problem in conservation of momentum and conservation of energy. So in this case, what we have is we have a block that is hanging from two strings, and then there is a bullet that's incoming, right? And so the bullet gets embedded in the block, and the block goes to a height. Some height, right? So it's goes to some height, right, with the bullet in there, right? So this one and the problem we solved before this, where the block gets embedded and then the block moves on, moves some distance d. Both of these methods can be practically used to find velocities of bullets, and so the block is raised to, let's say, a height h, and so let's say that this height is h, and so let's call the velocity of the incoming bullet v, and then when the bullet gets embedded in the block, let's call that v prime. So we're gonna use a similar process, and at first we're gonna apply conservation of momentum. So p initial is going to be equal to p final. It's again a perfect and elastic collision. The mass, let's call the mass of the block capital M. The mass of the bullet is small m. So initially only the bullet is moving, and then after the collision takes place, this is right after the collision takes place, they both move with some velocity v prime together. So we need again to find the velocity of the bullet, and we can get the velocity of the bullet and the block both in this case, and we'll see how that's the case. So let's call this equation 1. So m plus capital M divided by small m times v prime. So let's call this equation 1. Now we're going to apply conservation of energy. So now when the block starts over here, it has all kinetic energy, which is converted into potential energy. So apply energy conservation. So E initial is equal to E final, and again at the point where the bullet gets embedded in the block, it has all kinetic energy, and that's converted into all potential energy at this height. So we have m plus small m plus capital M, half, right, and then it moves with the velocity of v prime, right, squared, and then that is all converted into m plus m times g times h, and so this mass cancels out, right, and so you get v prime, the typical expression that we get for velocities. And so independent of the mass, this is independent of the mass, so v prime is 2g h. And so let's call this equation 2. And now what we can do is we can plug in this v prime, right? So plug 2 in 1, right? We get v. Did I call it v1? Okay, so it's just v. So v is equal to m plus capital M divided by m, and that's square root 2gh. Okay, so now let's bring in some numbers. Let's say that the mass of the bullet is and so I have this habit of first simplifying this equation, because in physics you can see a lot of things cancel out when you're simplifying equations. So that solves you a lot of time when you if you just simplify the equation first and then think about numbers. So the mass of the let's say that the mass of the bullet is 5 grams, which is 0.05 kilograms. The mass of the block, let's say, is 2 kilograms, and then let's say the height is 3 centimeters. So obviously we can measure the height in a particular situation. So 0.03. This is 0.03 meters. And so when you plug in these numbers, you get the velocity of the bullet to be around 307 meters per second. So that's the velocity of the bullet. And then you can also, since we know h, you can also get v prime. V prime is around 0.077 meters per second. So So this way we have both the velocity of the bullet, and you can see that v prime is a small number. You expect that because the block is quite heavy. When the bullet gets embedded, it moves with a small velocity. And so this problem nicely demonstrates how conservation of momentum and conservation of energy can be applied to a system.